Okay, good afternoon, everyone. Welcome to this seminar organized by the Productivity, Innovation and Entrepreneurship division of the OECD in the Science, Technology and Innovation Directorate. I'm Antoine Dechezleprêtre. I'll be chairing this seminar today. So we're very pleased to have Nahim bin Zahur. Nahim, welcome. Thanks so much for joining us today. So Nahim is an assistant professor at Queen's University in Canada. So he's an economist whose research lies at the intersection of industrial organization, energy and environmental economics and public policy. You got your PhD from Cornell University, not a bad place to study at. You've published extensively. I was very jealous looking at your webpage this morning before chairing this seminar. So papers in Review of Economic Studies, Review of Economics and Statistics, and you also have a long list of revise and resubmits to top journals. So I understand that this list is going to grow in the years to come, including the papers that you will present today. The committee we work for, the Committee on Innovation, Industry and Entrepreneurship, CIAE, works on. So that's why I invited you, Nahim, because industrial policy, innovation policy, the energy transition, global value chains, all of these topics are really at the heart of the work that we do with this committee on industry here. And so today you'll be presenting on the role of learning by doing, but also government policies in the massive reduction in battery costs for the EV industries that we've observed. So this is very, very interesting. We're also honored to have Mathias Reynaert from Toulouse School of Economics as the lead discussant for today's paper. So Mathias, you earned your PhD in economics at Leuven University and University of Antwerp. And since then, you've been at TSE, where you're now full professor of economics. Your work is very aligned with the work of Nahim, so between industrial organization and environmental economics. Just like Nahim, you also have a pretty impressive list of publications in similar top journals. So I think, really we have the perfect discussant for today's paper. So thanks again a lot, Mathias, for accepting our invitation. So before we hear from Nahim and then from Mathias, I just want to remind everyone of a couple of housekeeping rules. So the event is fully virtual, but you can ask questions through the Q&A feature in the Zoom application. You can also use the chat. And if you want to speak and to ask questions to the speaker after the presentation and the discussion, you can also raise your hand, and we have a technical team here who can enable your microphone and let you ask your questions directly. So we'll now turn to the presentation by Nahim. So you have 40 minutes for your presentation. Again, thank you very much for being with us today, and the floor is yours.
Thank you very much, Antoine, for the introduction, and it's a great pleasure to be able to present here. So let me share my slides and jump right in. So see if this screen works. Okay. So this is joint work with Panle Barwick, Shanjun Lee, and Hyuk-Sik Kwon, and this paper is about learning by doing and government policy in the global EV battery industry. So let me start off by way of motivation. So we know that one of the main barriers to the adoption of electric vehicles has been the high cost of the lithium-ion batteries that are used to power them. So depending on which time period we're talking about, this cost could go anywhere between 20 to 60% of the final EV price. Now, these costs have been declining sharply over time. So if you look at this picture, which is from the Bloomberg New Energy Finance, it kind of shows how there has been this 90% reduction in battery costs between 2010 and 2020, right? And these cost reductions kind of continue to this date. Now, what we are interested in understanding in this project is, how much of this cost reduction comes about from learning by doing, where by learning by doing, we think about this mechanism where as manufacturers gain more experience, their production costs decrease as they gain more and more experience. And so there have been some previous attempts to try to quantify learning at the industry level. And so sort of a typical estimate is that when industry cumulative production doubles, right? So when the industry doubles its experience, you get something like a 20 to 28% reduction in battery costs. But this could be due to learning by doing, but this could also be due to all kinds of other things that are not really to do with learning. So for example, it could be because there are scale economies, right? If you're larger, you can produce batteries more cheaply. This could be just due to technology getting better, which means that any firm, regardless of how much experience they have, might be able to produce batteries more cheaply as the industry advances. And so in this project, we're really trying to disentangle learning by doing from some of these other explanations for the cost reduction. And we think that's highly relevant, not just, it's interesting from an economic standpoint itself, but also it's highly relevant for understanding different classes of government policies. And so first of all, if you think about subsidies for EVs, right? These are subsidies that consumers get for purchasing electric vehicles. These are sort of widely utilized around the world. And in the presence of learning by doing, there's a potential extra benefit to these subsidies that we think hasn't been quite looked at in the past literature on EVs. And so the idea is that when you subsidize EVs, then there's a direct consequence, which is that consumers are going to purchase more EVs. But then in the presence of learning, what that means is that battery suppliers can now gain experience more quickly, right? So you subsidize EVs, there's more demand for batteries, battery suppliers go faster down their learning curve. And then depending on how large learning by doing is, that could mean that future learning is enhanced, and that could increase the future adoption of EVs. And so subsidies could have a long-term effect that's beyond just the direct impact on consumer purchases. And so that's one of the things that we really would like to understand in this project. To what extent do subsidies affect EV adoption and welfare when you take into account learning by doing effects? The second class of policies is a class that has become increasingly prominent in recent years, which is essentially policies that provide preferential treatment towards domestic battery producers. And so an early example of this was a whitelist policy that was employed by China, and that's actually going to be one of the policies that we're going to focus on in this project. So basically between 2016 and 2019, the Chinese government basically had this policy where for Chinese electric vehicles to qualify for subsidies, they would essentially have to procure batteries domestically from a government-approved whitelist of battery suppliers. This policy lasted between 2016 and 19, and it was scrapped eventually. But this type of policy, essentially what it did was it provided protection for Chinese battery suppliers, but that came potentially at the expense of battery suppliers in Japan, in Korea, that were looking to enter into the Chinese market. Now, these similar types of policies are now very much in discussion. And so if you look at the US IRA and the Inflation Reduction Act, we kind of see also these local content requirements, both on vehicle assembly as well as battery production. And so if you want to understand these types of policies that try to provide, this type of preferential treatment, learning by doing is sort of one important channel that we have to take into account, because one of the justifications for such a policy is that it's basically like an infant industry policy that tries to protect the domestic industry when it's, try to get it to advance on the learning curve faster. Of course, this could come at the expense of learning by overseas rivals, right? And so these effects are something that we would like to understand. And I think the final point I would like to make here is that all of these policies, when there is learning by doing, could generate cross-market spillovers that operate globally. And part of the reason is that, the whole supply chain for electric vehicles is highly global in nature, right? You've got batteries produced in one country, and then, EVs assembled in other countries. And so policies in one country can have spillovers in other countries. And so we have sort of two objectives in this project. The first is to quantify how much learning by doing is happening in battery production and how much of the cost reduction that we see comes from learning by doing. And then the second is to then translate that into an understanding of what impacts government policies have. So specifically, we're going to look at both these two classes of policies that are introduced. We'll look at the impact of consumer subsidies as well as these local content requirements, where we're going to specifically focus on this Chinese whitelist policy because that kind of happened during the sample period that we are studying, which is 2013 to 2020. And then it kind of provides a nice test case of what happens to the industry in the long term when one government decides to protect their own battery industry, potentially at the expense of everyone else. So I'll tell you a lot about how we methodologically try to address learning by doing and evaluate these policies. But one thing I should say up front is that one key challenge that we have is that our data set is not going to directly have model level battery costs. What we're instead going to have is data at the EV level on EV sales, EV prices, and then we know for each electric vehicle sold which battery supplier the battery is procured from. And so we're going to have to figure out a way to sort of back out the battery costs from the observed price of the EV, right? And so what we're essentially going to do is that we're going to deploy the structural I/O approach, where we're going to write down a model of competition in the global EV industry, which is going to feature both upstream battery pricing decisions by the battery suppliers. And that's essentially going to be, battery suppliers negotiate with EV manufacturers about the battery price, as well as downstream competition between the EV producers themselves. We're going to then take that structural model to the data that we have, which is going to have model level, EV prices, EV costs, EV prices, EV sales, as well as characteristics of the EVs and batteries. And then essentially through the structural model and through the data that we have, we're going to try to infer the margins that are earned both by the upstream battery suppliers as well as the downstream EV firms, and then recover the cost component and then split that into the vehicle cost and the battery cost. And then that's then going to allow us to examine learning by doing. Now there's a second empirical challenge, which is that suppose we have recovered this battery cost, now we would like to relate that to the battery maker's experience, right? So we would like to, basically estimate a learning curve where we try to see how do the battery costs change with experience, right? There's now going to be an endogeneity challenge where if we were just to do a simple regression of costs on experience, we might run into confounding factors. For example, it might be that there are some battery suppliers that are just very productive. They're just very good at producing batteries. It's nothing to do with experience, and that's what drives up their experience and drives down their costs. And so in order to deal with this, we're going to develop an instrumental variable strategy where we're going to basically come up with an instrument for experience, which is going to leverage the fact that different suppliers have different exposure to EV subsidies and this Chinese whitelist policy that shift the downstream demand while being plausibly uncorrelated with the unobserved costs that they have. Okay, so let me just now dive right into the paper. What I'm going to do for the rest of the talk is I'll tell you a little bit more about the industry, introduce the data, talk about the model and how we estimate the parameters, and then show you some results, and then finally turn to the policy counterfactuals that sort of motivated the talk. And so let me start off with a quick overview of battery production, where what we are going to focus on. And so essentially the way batteries are assembled is that there's first the battery cells are first produced. These are then assembled into modules. Modules are then assembled into packs, and then the pack is then combined into a battery system. That's ultimately what goes into the EV. And so our focus is going to be on this first part of this supply chain, which is the cell production. That's actually the major part of the cost of the battery. And this is a process that's actually surprisingly complex once you start learning about it. And so there are sorts of there are hundreds of different parameters in this production process that all need to be fine-tuned and optimized. And this is something that the industry sort of struggles with at the initial stage, and especially because each of these steps is highly critical and also highly sensitive to For example, clean room standards and purity. And so one of the examples that we learned was that when Panasonic and Tesla initially set up their factory, then what would happen is that the initial production would have about an 80 to 90% scrap rate. So about 80 to 90% of the batteries that they were producing, they would have to actually scrap because they didn't meet the standards. And then over time, they would figure out how to fine tune all these different processes, and then that's how they would get to a more acceptable scrap rate. And so we think that's the kind of thing that's happening when we talk about learning by doing. What I'll show you in this paper is sort of these abstract estimates of learning by doing, but behind the scenes, what we think is happening is that firms are figuring out how to fine-tune these processes. One thing to also keep in mind is that the technology is also changing all the time. There's new chemistries coming in, new production techniques. And so when new technologies come in, then firms might have to sort of recalibrate, and that also points to the importance of experience and learning. So now let me tell you about what data we use, because that's going to heavily inform the way that we do our analysis. And so the data that we have is essentially going to be model level EV sales and EV attributes. That's going to include the EV price. That's going to cover 13 countries from 2013 to 2020. This is going to include most of the major European markets. It's going to include China. It's going to include the US and Canada, as well as Japan. And overall, it's going to cover about 95% of global EV sales in this time period. Now, one thing I should mention is that we started this project in 2021. So, of course, by now, the industry has changed dramatically. We're only going to be able to speak to the data from 2013 to 2020, right? So the industry has exploded since then. So we're kind of looking at an early stage of the industry where learning by doing was very prominent. Now, what we also see in this data is we see the battery supplier for each of the EVs that's sold. And we also see different battery characteristics. So, for example, the battery capacity, which type of chemistry the battery operates on. And so from this, we know the experience of each battery supplier, right? So at each point in time, we know exactly who the battery supplier is for each EV. And so we can sort of see how battery experience evolves over time. And our strategy is essentially going to be to recover the battery cost from the EV price, which I'm going to talk about in a second. We also have data on battery plant location and the capacity of those plants as well. And finally, we're going to match this with data on various types of financial and non-financial incentives offered in different countries, which is going to tell us about subsidies, for example, or tax credits for EVs and things like that. Okay, so let me show a couple of descriptive charts before getting to the model. So the first thing I want to show is that battery supplier, the production of batteries is highly concentrated. And so this is a chart plotting cumulative production of the 6 biggest battery suppliers over time. And one thing to keep in mind is that these 6 suppliers basically account for about 75% of global production. And one of the things that there are a couple of things we see. First is we just see the huge growth in the industry production, but also the massive growth in experience of these big suppliers. And so if you look at, for example, this black light here, that's CATL, which is the largest manufacturer. This is one of the Chinese battery manufacturers. We also see, for example, LG, which is this blue line, and then BYD, which is a Chinese battery manufacturer as well that produces its own batteries. That's this orange line here. But overall, this is a highly concentrated industry where a lot of the production is taking place in China, in Japan, and in South Korea, right? So by these 6 manufacturers from these 3 countries. Now just to give you a sense of the supply chain, this is a Sankey diagram kind of showing the battery supplier network. So which battery suppliers sell to which EV manufacturers. Now the EV manufacturer is also fairly concentrated, especially once you look locally at different markets. And one thing to keep in mind here is that we see that each there's some element of vertical integration. For example, BYD only produces batteries for itself, but in general there's also a lot of cross linkages, right? So if you look at CATL, which is the largest manufacturer, they're selling to multiple different EV manufacturers, right? And so the way this is going to be important is that we're going to think about this market as not being fully vertically integrated, but rather it's a market where we have different battery suppliers negotiating with different EV makers, and that's going to inform the way that we model this industry. Now, the next two charts that I want to show you is to show you some evidence for learning by doing, as well as the effect of that whitelist policy that I talked about, which is a local content requirement in China. So first, what I plot here is, this is a picture where on the horizontal axis, we have the experience of battery suppliers. And so experience here is going to be measured in terms of how many batteries have they produced up until this date, right? So it's the cumulative production of batteries before the current date. On the vertical axis, what we have is we take the price data that we have, but we try to control for things that are not related to batteries. So we're going to control for EV characteristics, we're going to control for various kinds of fixed effects, the country, brand, and year fixed effects. What we're left with is going to be these price residuals that are going to reflect changes in the battery cost, right? So we can think of this as sort of a reduced form measure that reflects battery costs. And what we see here is that we see this downward relationship that kind of looks a bit like learning by doing, right? So we see that when you have battery suppliers that have more experience, which is the horizontal axis, then they tend to have lower battery costs as reflected in these price residuals. One other thing that we might notice here, which is interesting, is that we have also, these circles, these are for each battery supplier. We've sort of made the size of these circles proportional to the total amount of subsidy that they have received. And this kind of points at the identification strategy that we're going to employ later on, where the idea is that if you have been more exposed to subsidies in the past, that's going to drive up your experience, right? That's going to be a shock that drives up your experience. And that could then cause you to learn faster, right? And so we kind of see that reflected in this picture as well, that the very inexperienced suppliers are often those that haven't been much exposed to subsidies, and then as subsidy exposure increases, you sort of see the suppliers gain more experience, right? And so this sort of gives some reduced form evidence of learning by doing. This is, of course, not causal in any sense, because this is just, again, showing the raw correlation, right? And so the thing that we do in the actual analysis is to try to actually come up with an IV strategy that's going to pin down how much of this is learning by doing and how much of it is other factors that are not here. The second and sort of last descriptive chart I want to show you is just to show you the impact of that whitelist policy that I mentioned in China. So just to give you a reminder, this policy basically lasted from January 2016 to June 2019. And during this time period, EVs in China would only qualify for subsidies if the batteries are procured domestically, right? And so this first picture on the left, this shows you, this is a chart that plots the share of EV models that are sourcing batteries from Chinese suppliers at different points in time, right? So let me focus on the red line first. These are for EVs that are sold in China. And so what you can see is that before the whitelist policy, right, about 68% of Chinese EVs would get batteries domestically, right? So there was, there's definitely some foreign imports of batteries during that time, right? So Korean battery suppliers in particular were already exporting batteries to China. Once the whitelist policy comes in, then this share starts to increase and it goes all the way up to about 90%, right? So during this time period, there was a strong incentive not to get batteries from Korea or Japan, but to instead get batteries from Chinese battery suppliers. And so Chinese EV makers switched to Chinese battery suppliers during this time period. And the Chinese domestic share increased to 90%. And then even after the policy was removed, there was a slight decrease, but over time it stayed quite consistently high. Now, if you look at the share of Chinese battery suppliers among EVs that are sold outside of China, right, we also start to see that increase towards the end of our sample. And essentially, one of the things that we're going to show in the paper is that this is actually the period when Chinese battery makers really expanded their production and experience, and so they were able to advance down their learning curve really fast. And so that then potentially made them more competitive, which could explain this increase that we see at the end. And so kind of consistent with that, if I now look at the right-hand chart here, this is plotting the experience of some of the biggest battery manufacturers over time. So the red line plots the experience for BYD and CATL, which are the two biggest Chinese manufacturers, whereas the blue line here plots the experience of the four biggest non-Chinese manufacturers, which are going to be the Japanese and the two biggest Japanese and the two biggest Korean manufacturers. And you can kind of see that before 2016, the industry was actually dominated by these non-Chinese battery manufacturers, but during this whitelist period, the Chinese manufacturers really expanded and became the largest in the world. Okay. And so with that in mind, let me now turn to the, how we're going to model the industry and how we're going to estimate the cost, especially the learning by doing parameter. And so just to set the stage again, remember that we need to estimate learning by doing, for which we need battery cost data, which ideally we would just have data on battery cost, but this data is not, it's proprietary, it's not something that we can get. And so our strategy is going to be to infer the cost data from the prices of EVs, which we do see. So I'm going to tell you how that works in a second. We also need to estimate the impacts of different types of policies, right? We need to estimate the impacts of subsidies, the impact of this sorts of whitelist policies. And for that, we need to be able to do counterfactual simulations. And so what we're going to do is we're going to set up a model of the industry, which we're going to estimate to try to do both of these things. We're going to both estimate this model, which is going to involve estimating battery costs and learning by doing. And then we're going to take this model and then look at what happens when you change subsidies or when you shut down the whitelist policy. That's going to tell us about the impact of this policy. So the model is essentially going to have two basic components. There's going to be a demand side where consumers decide whether to buy an electric vehicle and then which EV to buy. And when they decide which EV to buy, they're going to pay attention to the EV price, the characteristics of the EV. So this is going to be a random coefficients VLP model that's going to incorporate a lot of consumer heterogeneity in the purchases. Now on the supply side, and that's what I'm mainly going to focus on in this talk, there's going to be sort of two main components to it. So there's going to be a downstream competition stage where EV producers decide how to set the prices for vehicles. So think about Tesla competing with Volkswagen and other EV manufacturers. And then there's going to be an upstream side of the industry, which is going to pin down how the battery prices are set. And for this, what we do in the paper is we explore sort of different ways in which these prices could be set. And so just to give you a schematic of how this is all going to work, and that's going to be important as well for informing our estimation strategy as well. So think about a set of battery suppliers. So, think about LG or Panasonic or Cartel, right? These battery suppliers, they're going to produce the battery, which is going to cost, that's going to mean that they're going to incur some battery cost, which we're going to call MCB, right? B is for battery. And the idea is that this cost is where there might potentially be learning by doing, right? So as the battery suppliers gain more and more experience, this cost might go down, right? Now, this is what we don't directly see in the data, right? We see something else. Now, what's going to happen then is that once they produce the batteries, they're going to sell it to the EV producers, right? So think about Tesla, right? We're going to denote EV producers by V, right? V is for vehicle. And there's going to be some way in which these prices are set, right? So in the paper, we explore all sorts of different models. For this talk, I'm just going to think about our baseline assumption, which is that there's going to be some bargaining process between these battery suppliers and the EV producers. They're going to bargain, and there's going to be some bargaining parameter, which we're going to call lambda, which is going to tell us how the profits are split between the battery supplier and the EV producers, right? And so through this bargaining process, that's going to pin down the battery price, which is then also going to pin down what is the markup that the battery suppliers earn on top of their cost, which we're going to call, that's what we're going to call MKB. MK is for markup. And then the EV producers, when they get the battery, they're also going to incur their own costs of assembling the EV and putting that together. That's going to be this vehicle cost, MCB, and then they're going to then compete in the downstream industry. There's going to be some, we're going to model that via some Bertrand-Nash competition, the idea being that they're going to compete in prices, and then if there's less competition, these prices might be higher. So that's going to pin down the markup for the vehicles, and then that's going to then, if we add these all up, then we get the EV price, which is what we see in the data, right? So part of the idea behind how we are going to estimate this model is that we're going to see data on the prices, and we're also going to see all sorts of data on the characteristics of the EVs, the characteristics of the batteries. And then our approach is going to be try to infer these markups, and then get rid of those. And then we're left with the sum of the battery cost and the vehicle cost. And then we can take that to the data and try to run a regression to understand where the learning by doing is coming from, as well as other things that could drive the cost. Okay. And so what I'll now do is I'll tell you a little bit more about the different elements of the model, and then I'll turn to the estimating equation, where I can then talk about how we deal with the different empirical challenges that we have. Okay, so our main assumption is going to be this bargaining assumption between the battery suppliers and EV makers. So the model that we're going to apply is one that's quite common, popular in empirical IO nowadays, which is this Nash-Nash bargaining model. And so the idea behind this is that we're going to have a set of battery suppliers and a set of EV makers. They're each going to negotiate over the battery price for their particular negotiation. So think about Tesla negotiating with Panasonic over the price of the batteries that Panasonic sells to Tesla. And then all these negotiations are going to happen in a Nash equilibrium across the market. And so that's kind of why it's called the Nash-Nash bargaining model. And this is going to happen simultaneously as the EV makers engage in downstream competition to set the EV price, right? So we've got the upstream negotiations over the battery price, as well as this downstream price setting between the EV firms. So the way the upstream negotiations are going to work is that the battery price, we're going to call that tau J. So J is for a given model, and then for each model, there might be potentially a different battery price. And technically, the way this negotiation is going to work is that each supplier is, the negotiation is basically going to choose the battery price that maximizes the Nash product of the gains from trade. And so the gains from trade, we can think of that as basically from the vehicle manufacturer's perspective, right? For this given negotiation, if that succeeds, then pi V is how much profits they make. If that negotiation fails, they can still sell all the other vehicles that they have, but they can't sell this particular vehicle because they couldn't find a battery supplier. And so that's going to give a different set of profits, which we're going to call DV, that's the disagreement profits. And so the difference between this is basically how much they're gaining from this particular negotiation taking place. And so in a similar way, we can define the profits for the battery supplier, the gains from the battery supplier. And what this Nash bargaining essentially does is to try to pick the price that maximizes this Nash product, where lambda B here is going to be the bargaining weight of the battery supplier. And so the way to think about this is that if lambda B is equal to 1, then the battery supplier gets all the profits from this negotiation. The EV maker has no markup. And then if lambda B is 0, then basically it's reversed, right? And so lambda B kind of governs how much of the profits go to the battery supplier and how much of the profits go to the EV maker. Okay, and so what we can do now is that we in the paper, we kind of work out this Nash product, and what we show is that the markup that's earned by the battery supplier can be written in this form, where it's basically going to be a function of this bargaining weight that we estimate, as well as this term here, MK bar B, which is something that we can construct once we've estimated demand, right? This is going to depend on, this is basically the battery markup when the bargaining is evenly split. And this is something that's known once we've estimated demand, right? And so that helps inform our estimating equation, where what we're going to do is that we're going to basically go back to this idea that we have the EV price, but we would like to recover from this the different components of it, right? So the way we're going to operationalize our estimation is that we'll take the EV price, for model J in country C at time t, so that's PJCT. We're going to subtract from that the markup earned by the vehicle manufacturer. So think about Tesla's markup, right? The margin that Tesla earns on each vehicle. That's going to be our left-hand side variable, our dependent variable. And then essentially we're going to run this regression where the first term that we have is going to be this battery markup term that I just showed you, where the unknown parameter here is going to be this bargaining weight. After that, we still have the different costs left. So there's going to be an EV cost. So that's going to be this term here. That's the cost of that's essentially the cost of producing the vehicle on top of the battery cost. And so here we're going to kind of include different vehicle attributes that might change the cost, right? So think about the fuel type, right? Whether it's a PHEV or a battery or pure battery EV, the size of the vehicle, the horsepower. We're also going to account for EV producer experience, because we're also thinking that they might be learning by doing by the EV producers themselves, which is separate from the battery producers. And we're also going to control for a range of fixed effects here that could account for different drivers of these costs, right? So we're going to have country fixed effects, brand fixed effects, as well as battery supplier and year fixed effects. And then finally, let me turn to the battery cost, which is going to be the key thing that we're really focusing on, because this is where the battery learning by doing takes place. The way we're going to operationalize this is that it's going to be the battery capacity multiplied by the per kilowatt hour cost of the battery. So each battery has a capacity which could be a certain number of kilowatt hour, which we see in the data. And then the cost of the battery per kilowatt hour, this is where we're going to allow for experience. And so if you look at this term here, this gamma naught times EBT, EBT here is going to be the experience of the battery supplier at any given point in time. And this exponent term, gamma E, that's going to tell us about learning by doing, right? So suppose that there was no learning by doing, then this gamma E would be 0. Now, if there is learning by doing, then this gamma E term is negative, meaning that as this experience term grows, this cost goes down, right? And so we kind of adopt this particular functional form because this is sort of common in the learning by doing literature. Now, what we're also going to allow for in our specifications is we're going to try to control for other things that could drive learning by doing, right? So we're going to have a time trend here which captures technological progress, and in the paper we also experiment with sort of a more flexible specification where we have year fixed effects. And then we're also going to control for chemistry of the battery, the capacity of the plant, which controls for scale economies. And then we're also going to include sort of measures of mineral prices, because the upstream cost of batteries might depend on, for example, the cost of lithium, right? And so this is the equation that we're going to take to the data. It sort of has a few different components, but the idea is that once you have recovered these markups, what we're left with is the EV cost and the battery cost. And then we have characteristics of the EVs and characteristics of the batteries to try to separate these, right? And so this is how we deal with our first empirical challenge, which is to recover the battery cost from the EV price that we have. Now, there's a second empirical challenge, which is if you think about this regression that we're doing, where we're basically relating the battery cost to the experience, if we were just to do OLS here, then we'd run into this endogeneity problem that we talked about before, right? And essentially the way that's going to happen, this is sort of a technical side, but I just want to give you the high level intuition behind this. So the idea is that if you think about one battery supplier's experience, that's going to be a function of their production on each of the models that they're selling to, right? So each battery supplier could be a supplier for many different EV models, right? So it's going to depend on how much they sell for each EV model, but also on how wide their network is, right? So if you think about a supplier like Catel, they're supplying to a range of different EV models, and so they gain a lot of experience from that. And so the endogeneity challenge here is that both of these elements, right, both their per vehicle sales as well as the overall network of their supply, those could both be correlated with unobserved costs, right? So if one supplier is very productive, they're going to be able to expand their network very quickly, and also each of their models will have higher sales because they have more productive costs and so cheaper batteries. And so what we're going to do is we're going to use an instrument for this experience, which is going to be, we're going to call that predicted experience. And essentially the idea is that we're going to basically replace the experience with the predicted experience, where both the network and the per vehicle sales are going to be instrumented, where basically we're going to replace the actual network that we see in the data with the predicted probabilities of selling to different EV models as a function of exogenous variables, which affect demand but not cost. So think about, for example, the initial supply chain of the industry during 2013, as well as the whitelist policy and home bias. And we're also going to exploit how the sales of the battery suppliers change as a function of the subsidies and and different exogenous attributes. And so basically the idea behind this is that different EV suppliers are differentially exposed to downstream subsidies depending on where they happen to be located in the initial part of the sample, right? And which suppliers they were selling to, which EV makers they were selling to in the initial part of the sample. And so if one country has very generous subsidies compared to another, that's going to differentially affect the experience of different battery suppliers. And that's going to provide an exogenous shock to the experience, which we can then use to understand how much learning by doing there is actually happening. Okay, and so with that, let me now turn to the results of the paper. Okay, so what I'll first do is I'll talk about the learning by doing estimates, and then I'll turn to what that means for policy. Okay, and so I'm going to focus on sort of looking at the battery side of production here in the interest of time. And so what we're sort of really interested in this is in this learning parameter, right, which is going to capture how much learning by doing is taking place. And so we sort of explore different specifications here. We're going to start off with a specification where we don't have that many controls. And here we see that learning is, the learning effect is quite strong. And then what we're going to do is we're going to gradually control for, a time trend. We're going to control for scale economies by controlling for capacity of the plants. And then we're also going to allow for the fact that EV manufacturers might have experience, which is this last variable here. And then that sort of gives us our final estimate in column 4, which is our preferred sort of estimate. So under a preferred estimate, essentially what we're finding is that when you increase a battery supplier experience by 1%, you get about a 0.14% reduction in battery cost. And that translates into a learning rate of about 9.2%, right? So the idea is that if your experience doubles, then your cost goes down by about 9.2%, right? Now, this is a little bit on the low end of estimates of learning by doing from a range of different industries that have been found. And one of the things that we really want to emphasize in this paper is that it's really important to account for technological progress and other things that are going on, because without that, we would be also finding a very high learning rate, right? But what we're finding is something more modest, around 9%. Now, despite the learning rate being on the face of it kind of modest, we actually find it's quantitatively quite important, right? So we find that it accounts for about 40% of the overall cost reduction between 2014 and 2020, right? And just to quickly talk about some of the other things that are going on, we find a meaningful negative time trend capturing technological progress, and that accounts for about 34% of cost reductions. And we also find that there's sizable learning by doing by the EV manufacturers, but quantitatively, most of the learning by doing, most of the important learning effects are coming from the battery suppliers in this industry. Finally, we find bargaining, that bargaining is more skewed towards the EV makers, so the battery suppliers have a bargaining rate of about 0.3, which implies sort of plausible upstream markups. So there are a lot of robustness checks that we do in the paper, which I won't really go into in the interest of time. But one of the things I should mention is that we do have some evidence that there's spillovers of learning across firms, but we don't find that to be statistically significant. So for baseline analysis, we're going to sort of go with our main specification where learning is within firm, right? So each firm learns, but the spillovers, we don't really find convincing evidence of that. So we're not going to use that for policy simulations. Okay, and so just one chart before I get to the counterfactual analysis, just to show you the importance of learning, right? So this is plotting the learning component of the battery cost across different battery suppliers. So the red line here is for Chinese battery suppliers, and then the black and blue lines are for Korean and Japanese battery makers. And what we see is that initially there was this sort of cost difference between the three countries, but then over time, as the Chinese manufacturers advance faster than the learning curve, they actually catch up and start to become competitive with Japanese and Korean manufacturers by the end of the sample period. And one of the things that we do in the counterfactuals is explore how much of that comes from this whitelist policy that we talked about. Okay, so let me now turn to our policy simulations, where there's basically two classes of policies that we're interested in. One is the effect of subsidies accounting for learning by doing. And the second is the effect of these domestic content requirements, right, which are policies that protect domestic battery industries. And so first what we'll do is we'll look at subsidies. And so I want to first show you how subsidies affect EV sales over time and how that is affected by learning. Okay, so the first thing that we do here is this is just a chart of EV sales over time, and not thinking about subsidies at all. This is just saying that what is the effect of learning by doing on EV sales, right? And so learning itself increased sales by almost 100% during the sample period, right? So without learning by doing on battery manufacturing side, EV sales would grow much more slowly, right? And so this is sort of done by shutting down subsidies. We're just going to try to look at learning here. The next thing that we do is we say, okay, what would happen to the industry if there was the learning by doing, but governments were to subsidize EVs, right? At the same rate that we saw in the data, right, in the observed world. And what we see is that there is a sizable increase in sales. Subsidies would have increased sales by about 28%. But if we now incorporate learning by doing as well, we find that this effect is much larger, right? So once we take into account that there is learning by doing present, now we have this extra channel where you subsidize the industry today. That's going to make the battery suppliers more efficient tomorrow, which is going to boost sales tomorrow. Once we take that multiplier effect into account, we find that subsidies actually increase sales by about 55%, right? So more than double the estimate that we found, right? So this kind of goes to show that it's really important to take into account this battery learning by doing when we think about evaluating these subsidies, right? And so what we do next is that we want to understand the welfare impacts of subsidies in the long run, accounting for learning by doing. And so what we're going to do is we're going to examine this separately for sort of different markets, right? So we're going to start off with subsidies by the US, right? So just to see how that affects learning by doing, but also how that spills over across the rest of the world, okay? So this is, basically a counterfactual where we say, okay, what if the US wouldn't have subsidized EVs, right? What is and that sort of tells us, by comparing that to the baseline, we can then see what is the net effect of US subsidies on on North American welfare, but also on welfare of consumers and producers around the world, okay? And so the first thing that we see is obviously that US subsidies are going to improve domestic consumer surplus and profits within North America, right? But then we also see that that actually benefits battery suppliers in Japan and South Korea because they're able to accelerate faster than their learning curve, and so their profits go up. And we actually see, and this is sort of an interesting spillover effect, that we see that this benefits consumers in Europe, right? And that's because the same suppliers, Japanese and Korean suppliers that are supplying to the US, they're actually also selling batteries to Europe. And so European consumers actually benefit, and European EV makers also benefit from North American subsidies. We also kind of see, and so actually if we do a net welfare calculation, right, the global welfare gain is almost double that goes to North America, right? So about 50% of welfare gains from US subsidies are actually coming from these cross-country spillovers, right? And so one of the points that we're trying to make in this paper is that in the presence of learning by doing, these spillovers effects are actually really important, right? Because these battery supply chain works through this global supply chain where battery makers in one country can leverage the experience that they gained in some other country. And so we kind of see a similar effect for European subsidies as well. So, European subsidies sort of have, obviously have a strong benefit within Europe as well, and they benefit Japanese and Korean manufacturers. But they also then benefit consumers and EV producers in North America and China, more so in North America because the Chinese EV market tends to be more self-contained, right? So there's less presence of these Japanese and Korean battery manufacturers that are benefiting from European subsidies. So now finally, if we turn to Chinese subsidies, we actually see that we see some spillovers here as well, but the spillovers are actually much more limited. And this is because of the nature of the Chinese battery supply chain, where during this period, at least much of the supply chain was concentrated within China. And so even though Chinese subsidies benefit Chinese battery suppliers and allow them to learn faster, this only has sort of small, modest benefits to European and North American markets during this time period. Okay, and so the final policy I want to look at is this whitelist policy of China, which basically protected their domestic battery industry, but then that came at the expense of Japanese and Korean manufacturers. And so what we actually find is that this policy led to a large improvement in battery profits within China, so it benefited the Chinese battery suppliers. But this came at the expense of battery suppliers in Japan and Korea. They were unable to sell in China. And that actually led to negative welfare consequences for Europe and North American consumers as well, right? So, since the Japanese and Korean manufacturers were, slower to get down their learning curve because of this policy, that then ended up hurting consumers in Europe and consumers in North America. And so what we actually end up finding is that there is an overall welfare gain to China from this policy, but there's a net welfare loss from this policy, right? So although China benefits from this policy by basically advancing learning by doing within their industry, this comes at the expense of the rest of the world, and the net welfare effect of this type of policy is actually negative. Another thing that we actually find is that, I kind of showed you how Chinese subsidies have some spillover benefits. We actually find that once we take the whitelist into account, it actually wipes out the spillover benefit to the rest of the world, right? So the rest of the world actually ends up being hurt by Chinese subsidies once the whitelist policy is in place. Finally, one last thing I want to emphasize is that all of these effects are amplified by the presence of learning, right? So with learning percent, the subsidies have much larger welfare impacts and spillovers. But also this sort of whitelist policy has less strong effects, it has stronger effects in the presence of learning by doing, right? So the negative effects of this whitelist policy would be smaller if there was the learning by doing. Okay? And so with that, let me conclude. So just to sort of wrap up, so we find the learning weight that's a little bit lower than existing estimates, but learning ends up being very important. It accounts for 40% of the overall cost reduction. And what we find is that subsidies have large positive spillovers to the rest of the world, but policies that protect the domestic battery industry, such as these whitelist policy or local content requirements, they could actually have negative effects on global welfare, where they might benefit the country that's implementing the policy, but that might come at the expense of other consumers out there. So thank you very much, and I'm really looking forward to Mathias's discussion and the Q&A afterwards. Thanks.
Thank you so much, Nahim, for the great presentation. I'll turn to Mathias straight away now for the discussion, and then I'll open up the floor for questions.
Thanks a lot, Antoine. Sorry, I was freezing for a second. Thanks a lot, Antoine, and thanks a lot, Nahim, for the excellent presentation. It's a pleasure to be here and to discuss this paper. I really like this paper as a proof. The moment it was released 2 years ago, I was teaching an IO environmental course, and I immediately included in the reading list for my PhD students to dig into the paper and look at all the details, because it's both from a methodological perspective very interesting, and also from a policy perspective a super relevant paper. And so it's a pleasure to be discussing this. So a central fact of the EV transition is this battery costs that have dramatically come down. And so what this paper is going to try and do is come in and try to study learning by doing in battery production. And so how important is the experience of manufacturing quantity itself. And so it's then going to also think about the interaction between two policy tools, demand subsidies and trade restrictions or local content requirements, and how those are going to interact with learning by doing. So that's the goal of the paper. In order to do that, it's going to use rich data. So there's a lot of studies that focus on one country. This paper does the whole globe. Basically, it has global EV demand and very important global battery production. And so we're really going to think about a global supply chain and how these policies in different parts of the world are going to interact with that supply chain. Then on the demand side, there's going to be consumers in every country choosing their vehicle. On the supply side, it's going to be firms that are going to produce EVs. And they are going to bargain for their inputs, which are the batteries. And based on that bargain, they're going to obtain batteries and then going to sell their EVs with the batteries to consumers. And so as Nahim explained very clearly, the crucial difficulty is that in a lot of data, we don't observe marginal costs, nor the marginal cost of production, nor the marginal cost of the battery. And so the main methodological focus of the paper is to tease out these marginal costs, and also then to basically think about how these marginal costs are changing with mass-produced quantity that is capturing the learning by doing of these firms. So it's interesting that this is a very dynamic question, but the paper isn't very dynamic. It's kind of a repeated cross-section of demands. And so what we are going to keep track of between the different years is how much we have produced up until that time. And then we update the production, and that's basically for every firm. The past production is the learning by doing that we are going to take upon. And so I think it's really neat that the paper is very pragmatic here and does something very simple, but it's also important, I think, to take into account that we are not taking into account a lot of other dynamic things that are going on, forward-looking pricing, entry dynamics, the way how these supply networks are formed dynamically, etc. That is not in the paper. It would also be very complicated to model. And I think what this paper succeeds in very neatly is doing it with a slightly simple standard static demand model to get such rich insights. So what is very important to see is that EV policy is now not just demand policy, but it really becomes industrial policy. Batteries are costly to produce, and the production is concentrated in a couple of large manufacturers. So you have the Japanese, the Koreans, and then more recently the massive Chinese producers. And so it's very obvious that these producers are very much impacted by the policy decisions of their governments. And so in that context, we are going to ask several research questions about learning by doing, about how demand affects future costs, and about who captures the gains from learning and how these trade policies are going to for me, the battery cost decline it's just striking. I remember finishing my PhD in 2014-15, and that was like the time when it was still very uncertain whether EVs would be the future or not. And one argument that I also pronounced myself as well, that these battery costs are so high, it's hard to imagine EVs really becoming competitive without massive government intervention. Well, we had substantial government intervention, but with that government intervention, production costs of batteries declined by 90%, a factor of 10. And so that's just mind-boggling when you look at these numbers and these cost declines. And so what this paper identifies is that almost half of that cost decline is coming from learning by doing, while the other half is coming from technology adoption. And so I think that the paper estimates a relatively modest learning by doing rate. Every time the production doubles, there's a 10% decline in production costs for batteries. If you think about other industries that were named, such as shipping, well, it takes a while before we produce double the amount of ships. But in EVs, it's going so fast because we're on this exponential growth also. And so production and demand are in terms of quantity, doubling at a very, very rapid rate. And so that also means that we are going super fast down this learning curve. And that really is mind-boggling to look at in terms of results. So how do we interpret from a welfare perspective this learning mechanism? It's very important that we focus on within battery suppliers. And so when you take a first look at the paper, you might think, well, why do we need policy then? Because the typical reason to have policy in learning by doing is with spillover. So I have learning by doing, and I do not internalize that some of that learning by doing spills over to my competitors who will also be more productive. So that channel is completely, they estimated that, as Nahim pointed out, it's not significant. And so they don't consider that channel, which is a typical policy channel, to think about subsidizing. They shut it down in counterfactuals. Where are all the welfare gains coming from then? Well, the reason why these upstream battery manufacturers are not rapidly investing in or rapidly enough investing in producing quantity and going down the learning curve is that there's a market, an appropriability problem. They do not capture all of the gains, welfare gains from producing a battery. There are the EV producers themselves and the consumer surplus that they do not take into account. So that is the key reason why the subsidies drive such welfare. Okay, and so then subsidies really become industrial policy in the sense that the subsidies immediately affect EV sales. That increases supplier experience. That then drives down battery costs in the next year, and that leads you to have lower EV prices. And so it's important to see that this is then also allowing us to have spillovers across borders, because these costs battery costs are available, these low battery costs in all countries. And also across time, this is there for multiple periods. Now we have efficient manufacturers. Okay, and so Nahim, and I'm going to skip this in the interest of time, and very clearly pointed out that with learning, subsidies are just a lot more powerful instruments than just evaluated without the learning. And then what's very interesting about the paper is these global spillovers that really rely on basically where the manufacturing takes place. So the US, Europe rely a lot on Korea and Japan, and the Chinese consumers, manufacturers rely more on Chinese manufacturing. And so when we do something in the US, in Europe, or in Japan and Korea, that spills over tremendously across these regions, and that's less so for the Chinese. So then the final policy that is looked at is this whitelist. And so the whitelist is basically requiring Chinese manufacturers to source locally from Chinese battery producers. And this is a policy that I would say is kind of popular, and there's talk across the world of copying this. The US has been trying to copy this. In Europe, there's also talk about copying this. And when we look at the paper and you read the paper diagonally, you would say, well, that's a great idea. In China, it was welfare improving, and China managed to basically get to scale because of this policy in combination with demand subsidies. But I think that you need to read the paper very carefully, and then I come away with actually the opposite policy conclusion, that it would not be beneficial for the rest of the world currently to copy this. And what's really crucial here is to look at the timing of this whitelist policy. And China introduced this whitelist policy at a moment when the Japanese and the Koreans were not super far on the learning curve yet. They still had a lot of distance to cover. And B, China could combine this with massive scale and was growing very rapidly in terms of EVs produced. And the combination of these two things, I think massive expected sales growth together with being still relatively early on the EV growth, these are the two elements combined that basically led this to be a successful policy for the Chinese and increasing Chinese welfare. And so when I think of the implications of this for the rest of the world, outside of China, Japan, and Korea, is that production location matters when it really is able to change the accumulation of frontier manufacturing capability. Another way to say this is that we're simply too late in the rest of the world. These manufacturers now have such scale that I think it's very difficult for even the full US market to catch up with Chinese, Korean, and Japanese manufacturers. The frontier is basically gone, and going to the frontier will cost you tremendous amounts of government money in terms of subsidy. And so we are going to have very inefficient policies that are very expensive in order to try and have domestic battery production. And so I think the policy debate in the rest of the world should change from basically these whitelist policies in combination with subsidies to thinking much more about how we can get Chinese technology and Japanese and Korean technology into the rest of the world to manufacture if it's needed, and we cannot ship batteries across the world on ships, and we want to have local manufacturing. We need to think about foreign direct investment, joint ventures, factory commissioning expertise, exchange programs, in terms of supplier ecosystems to get that knowledge into our local manufacturing systems. And I think that is the only way to get basically battery production in the rest. So that's kind of my policy interpretation of the counterfactuals that Nahim has presented. And so the main takeaways for me is that this is a super nice paper that really focuses on this very important policy. The learning by doing magnitude is mind-boggling and very impressive. And then there are very interesting trade-offs to look at in the policy space. And if you have some time later tonight after this presentation, I think it's really useful to open the paper and to look at the counterfactual tables and to read these numbers in detail and to really think about what's going on. It's really a super interesting thing. So, thanks a lot.
Thanks so much, Mathias, for the great discussion. I see there's a couple of questions in the chat, so I'll ask them in a minute. But perhaps Nahim, you want to react first to Mathias' point? Maybe, I mean, I would love to hear your thoughts on these implications of your results for current discussions in terms of these local content requirements, and whether what might have made sense in China in 2016 would still make sense or be extremely costly, as Mathias just said, for a region like Europe, which is far behind the frontier.
Yes, no, so definitely. So first, thanks a lot, Mathias. That was an excellent discussion. I think there are parts of the economics that you really explained much better than I was able to. So, and I think really the point about the timing of the step policy is super important, and that's actually one of the things that we tried to do in the paper as well, to see if China had delayed the whitelist policy, then would they still have had the same success domestically? And we actually find they don't. And I think basically I'm sort of in agreement with the way that Mathias laid out the economics of this, that this is when you have learning by doing, then it's really sort of key to intervene at sort of an early stage. And I think late stage interventions are much more tricky in the way that that Matthias was mentioning, for sure.
Thanks. Josh the Lion, one of our colleagues, had a question that he put in the chat, but Josh, you might as well just ask the question directly to Nahim. I see Shai has let you enter the room now.
Do you hear me?
Yes, we can hear you.
Okay, I don't think I can put the video, but okay. Thanks, firstly, it was super interesting. I think you mentioned very quickly that you focus on the within firm learning by doing component, but I don't know if you said you already did, or you could extend it to include between firm learning by doing. I was just wondering like how you model that, and like how you'd expect these effects to materialize. Like, do you model that as being stronger like within a country, and if so, like do you expect these effects to be strong, like to amplify the benefits to China, like where you have these very well developed battery supply chain, and then like what could policymakers do to help like maximize the gains from these learning by doing channels between firms? But thanks again, it was super interesting.
Right, great. So as actually we did we did try to model between firm learning, and the way we did that is actually exactly the way you mentioned. So we kind of thought about it as if for a Chinese battery firm, then maybe you can learn from other Chinese firms that from their experience, right? So the way we basically operationalized that was to think about my learning as consisting of my experience plus some coefficient times the experience of other firms within my same country. And then that's the one where we're kind of hesitant to say too much about it, because we did find there are positive spillovers, exactly the way you might expect, that certain part of my learning is actually coming from learning from from the experience of other firms in my country. But the estimate was sort of noisy, so we didn't sort of really push on that too much. But if you were to take that estimate that we have at face value, then what we actually find is that for the biggest firms, it doesn't matter so much, but for the small firms, and actually, this is an industry where, although I talked a lot about the 6 big firms, there are actually about 30 or so other manufacturers that were small in our sample, but some of them are becoming quite big now. And we actually find for them, a big part of their learning comes from, learning from others, from other firms. And what we know anecdotally is that this sort of thing is probably happening quite a bit within the industry. So, for example, within China, we talked to some of the smaller battery firms, and they actually talk about how some of their key engineers would be trained at Catel, which is the biggest battery maker, and then they would bring some of their know-how when they move jobs. And so we think those are the types of channels that might lead to knowledge transmission, right? So firms, first of all, there are sort of joint ventures between firms which could facilitate it, right? So that's something that we don't really have the ability to do statistically within this paper. But what might happen is that an EV manufacturer might sign deals with multiple battery makers, and so that might be one way in which know-how travels. Or when workers go from one firm to another, or when managers move from one firm to another, these are channels that could contribute to know-how. I think there's a big open question as to exactly how policy could target those channels. I don't have too much to say about that, at least from the standpoint of our paper, because we don't really have a convincing, a statistical estimate of that spillover, right? So we're not really able to directly operationalize that in our analysis.
That's great, thanks.
Yeah, because I think the policy implication, that if these externalities they accrue only at the large firms to the small, if the policy implication is that you need to subsidize only those large firms where those spillovers accrue, it's a bit hard to sell.
Exactly. Yeah. Because also I think one thing to keep in mind is that there's a big worry that with this type of Chinese policy as well, that it might lead to high concentration of the industry in the long term, right? And that's a negative consequence. So I think that's the other drawback of this type of industry policy, that we worry about a duopoly or monopoly. And currently we're in a situation where the two biggest Chinese firms actually control a large portion of global production, which the future implications of that are something that we're not, we don't know what will happen right in the future.
Yeah, this is the dynamics part that Mathias mentioned at the beginning of his intervention. So I'm going to ask you another question, Nahim, that came through the chat, and then I have a couple of questions myself. So the question about input cost, and in particular these critical raw materials that are key for the production of batteries. And then the question is about whether you've considered the preferential access to critical raw minerals that Chinese firms had, and how that might have also contributed to lowering battery production costs along the subsidies and the learning by doing, which you already consider. I don't know if you have anything to say to that.
Yeah, no, I think this is a really great question, and I think that's something that probably our analysis doesn't go too deep into that aspect of it. What we do account for is we have data on sort of the main minerals used in batteries, for example, lithium and some of the other main components. So we do control for the prices of those by country, right? So we do account for that, but I think behind the scenes there are some of these critical minerals that are, for example, rare earths that are important for EVs, that much of the production is concentrated within China, right? And so that's something that we don't have direct data on, so we're not directly accounting for that. I would say one thing though, which is that so China sort of had control of rare earth minerals, way back in before our analysis started. So even by 2010, China already had almost a monopoly for many of the critical rare earths. And despite that, we still actually see that at the start of our sample period, Chinese battery costs were not that competitive with Japanese and Korean manufacturers. And it was only after the whitelist policy sort of came in and there was this big increase in learning that we actually see them start to be competitive. So this gives us some idea that the minerals are the preferential access to these minerals is probably important, but maybe not first order in driving the type of economics that we see in the paper. Because if that was the case, then maybe we would have seen Chinese makers already have an advantage even as early as 2015.
One question that I had listening to your presentation, Nahim, was, so I know you have a pretty short sample, time period for the analysis, but I was wondering, I would expect the contribution of learning by doing and of, technological change to vary over time with, larger contribution of technological change in the beginning and maybe larger for learning by doing. And so have you looked at whether these average 9% of learning rate that you estimate is, has changed over time? Because I'm wondering, like, if you were to estimate it today, for example, what, would you expect to see? Is this learning rate, going down or up? Were you able to look into this?
So the learning rate, I think because of the way that our panel, we have just this, we have a 7-year panel of, there's about 40 battery firms. It's a little bit difficult to allow for time-varying learning rate. What we did try was sort of different groups of firms and, the big firms versus the smaller firms to see whether their learning rates are different. And that's something we didn't really find much evidence of. I think if we had a longer time, but especially if we had recent data, I think we would have loved to extend this analysis to the recent period, because since 2020 the industry has expanded so much that it would be interesting to see if the learning kind of continues. I think about your other question about technological progress versus the role of learning. So our basic specification sort of has technological progress happening sort of linearly every year. This is just something that we do to keep it simple, but we also have a specification where it's a little bit more flexible, and we kind of find that the learning effects sort of take a while to kick in to start to really contribute to cost reductions, because even the learning for each firm is like faster when they're initially expanding their experience, But there are many firms that come in towards the later part of the period. So we actually see learning effects throughout our sample, not just at the initial stage. I don't know how much that answers the question. I think we do, but we don't really have the power to do learning for the first part of the sample versus the second part of the sample.
Yeah. Okay, I see. But like intuitively, would you expect this learning rate, until now to have continued at the same pace, or do you think it's like if you were to estimate it today with today's data, would it be? Do you think it would be higher or lower?
So it's a bit hard to speculate. Like we do see that the battery costs, the 90% that we saw, we haven't seen the same 90% since then, right? But then there have been, there's been COVID shocks, and there was a huge shock to the mineral prices, right? So it's without hard data, it's hard to say. But many of the processes that we're thinking of, we think it's a lot of it would be once a firm is experienced enough, they would probably, like this fine-tuning process that we're talking about, right? This is something that, once they've done that to a sufficient degree, we wouldn't necessarily expect it to continue at the same rate. And so in a way that's kind of captured in our specification, because the idea is that after you have doubled experience a few times, it's going to be really expensive to double it again, right? So in a way it does capture that initially, producing a few more EVs gives you a few more batteries gives you a lot of learning. And then later on, once you have a lot of experience, then you really need to go above and beyond to get the same 9%.
Yeah, makes sense. Okay. And can you also speak a bit more about the technological change and the role of policies there? I'm thinking of the policy package, and okay, you have these demand side subsidies plus these local content, requirements sort of policy in China, but obviously the other important, possible element of policy is like support for R&D. And how important that should be in relation to those dozens of billions of subsidies on the demand side. I know your paper doesn't really speak to this, but still I'm curious to hear what whether you have any estimate of how much was spent more on this R&D side, and whether you think that policy package is was too much focused on demand side or not.
That's a really good point. So what I will say about this is we did find in the paper, it's sort of hidden in the appendix, that the firms that have done more patenting, they seem to have lower costs. And so it's sort of suggestive that, technological progress, not just at the industry level, but at the firm levels is also important. And so any policy that could, push that forward could have really important welfare impacts, particularly because, a lot of the, unlike learning, which we seem to find that, a lot of the learning is firm specific, whereas technological progress would be something that has wider benefits across the industry. And that's where we would expect some of these market failures of appropriability to be even more important, right? Now we have some other work where we actually find that industrial policy tends to have impacts on, technological progress within this sector as well. So we kind of looked at, like countries that do more industrial policy within the EV sector. We see that firms in those firms do more patenting, both in the battery sector as well as both the battery firms as well as the EV firms. So that also points to, it's not just R&D policy that could drive innovation, but it could also be just regular industrial policy could also drive innovation. And then there's an open question about which one is actually more effective, right? Which is the type of policy we should be using. I think there's definitely room for more research in this area to try to give precise answers to these types of questions.
Okay, so that will be your next paper, or our next paper. It's a question that is of high importance to this committee of industry here, as you can imagine. Okay, Nahim, I don't see any more questions in the room, so I think we'll end the seminar now. Thank you so much again for having been with us today from from Canada. Thank you again a lot to Mathias as well for the great discussion. And I wish both of you and all of our participants a great summer. We'll be back with the next edition of this webinar in September, and the next speaker will be announced very soon. Thank you again, everyone, and especially you, Nahim and Mathias. Bye bye.
Thank you very much. It was a pleasure.